In 1926, physicists discovered something that should not have been possible. A single particle, left alone, does not exist in one place. It exists in many places at once, a smear of possibility called a wave function. Only when it is observed does it snap into a single, definite location. This is the observer effect. And for 100 years it has haunted physics with an uncomfortable question. What counts as an observer? Does it have to be a conscious mind, or will any measuring device do? Most physicists will tell you the second answer is correct. A detector, a photographic plate, even a stray air molecule can cause what's called decoherence, the collapse of possibility into fact. Consciousness is not required. The mystery, they say, is just badly worded. But a smaller group of physicists and philosophers were never satisfied with that answer, and their reasoning takes us somewhere strange. In the 1990s, the physicist Roger Penrose and the anesthesiologist Stuart Hameroff proposed something radical. They suggested that consciousness itself might be a quantum process, that inside neurons, structures called microtubules are small enough and isolated enough to sustain quantum superposition, and that when those quantum states collapse in a very specific gravity-influenced way, that collapse is what we experience as a conscious moment. They called it orchestrated objective reduction, ORC-OR for short. Under this theory, a thought is not just electricity moving through a wet 3-pound organ. It is thousands of tiny quantum events collapsing in careful sequence, orchestrated like a symphony. It's a beautiful idea. It is also deeply controversial. The loudest objection has a name: decoherence. Quantum states are fragile. They fall apart the instant they interact with a warm, wet, noisy environment. And few environments are warmer, wetter, or noisier than the human brain. Critics calculated that any quantum coherence in microtubules should collapse in a fraction of a trillionth of a second. Far too fast, they argued, to do anything as slow and complicated as generating a thought. For 2 decades, that calculation was treated as the final word. Then in 2013 and after, laboratory experiments began finding warm quantum effects in unexpected places, in the way plants capture light during photosynthesis, and in the way migratory birds may sense magnetic fields. Biology, it turned out, was better at protecting fragile quantum states than anyone had assumed. The door Penrose and Hameroff opened didn't close. It just got harder to walk through. Here is why any of this matters beyond neuroscience. If consciousness depends on a specific quantum process happening in biological tissue, then a computer built from silicon and electricity, no matter how sophisticated its software, may be structurally incapable of consciousness. Not because it isn't smart enough, because it isn't made of the right stuff. That would mean every large language model, every neural network, every future artificial mind built the way we currently build them is running an extremely convincing simulation of a mind with nobody actually home. Of course, that conclusion rests on OR being correct, and most physicists remain unconvinced. But even the skeptics admit something unsettling. We do not have a working theory of how matter produces experience. We have equations that predict outcomes with extraordinary precision, and we have the felt reality of being aware. And between those two things sits an explanatory gap that a century of physics has not closed. Maybe consciousness will turn out to be quantum mechanical after all. Maybe it will turn out to be something classical that only looks mysterious because we're standing too close to it. Or maybe, and this is the possibility physics finds hardest to sit with,